Today, we're going to tackle one of the most powerful and, honestly, coolest ideas in all of science and math, the Fourier Transform. This is a tool that literally lets us see the hidden reality behind everything, from the music you stream to the medical scans that can save your life. So, let's dive in. So, let me start with a question for you. What on earth could a musical chord possibly have in common with an MRI scan? I mean, one is art, pure creativity. The other is high-tech medicine. They seem like they're from completely different universes, right? Well, what if I told you they're both built on the exact same mathematical idea?
Yep, that's the link. There's this thing that acts like a mathematical prism. You know how a glass prism can take a beam of plain white light and split it open into a beautiful rainbow of colors? The Fourier Transform does the same thing, but for any signal. It takes something that looks complex and messy, and it reveals all the simple, pure ingredients hiding inside.
Okay, so let's get into this. What does it actually mean to have a prism for signals? What is this thing really doing? Well, here's the core of it. The Fourier Transform is a way of taking any complicated signal, and I mean any signal, like the sound of my voice, a radio wave, even the data that makes up a digital picture, and it breaks it down into a list of simple, pure frequencies.
The best way to think about it is like a recipe. You taste a delicious cake, and it just tastes like, well, cake. But the Fourier Transform is like the chef, who can taste it and tell you the exact recipe. 2 cups of flour, 1 cup of sugar, a dash of vanilla, except instead of flour and sugar, the ingredients for a wave are its pure frequency.
And music is the perfect example of this. Look on the left, that squiggly, jagged line, that's the actual waveform of a C major chord. It's complex, it's messy, that's what hits your eardrum. But the Fourier Transform looks at that mess and says, oh, I know what that is, and it spits out the clean, simple waves on the right, the individual notes, C, E, and G, that you're actually hearing. It finds the music inside the noise.
So this brings us to a really crucial idea. The transform gives us 2 totally different ways of looking at the same thing. We can look at it through the lens of time or through the lens of frequency.
First, you've got the time domain. Now, this is the one we're all used to. It's the normal way we experience the world. It's a graph that just shows how a signal gets stronger or weaker from one moment to the next. That messy chord waveform we just saw, that was a picture of the chord in the time domain.
But then, the Fourier Transform lets us jump into a whole different world, the frequency domain. This is the prism's view. It completely ignores when things happen. Instead, it just shows us that recipe we talked about. It tells us what frequencies are in the signal and how much of each one there is. And this table just lays it out perfectly. The time domain asks when something happened. That's like hearing the sound of the chord being played. But the frequency domain asks what is it made of. That's like looking at the sheet music and seeing the individual notes written down. Same event, just 2 completely different but equally true ways of describing.
And I gotta tell you, this is not just some neat party trick for mathematicians. This ability to flip back and forth between time and frequency, it's the engine that powers so much of our modern technology.
Just think about the stuff you use every single day. You know how an MP3 file can be so much smaller than a CD file? It uses the Fourier Transform to find all the frequencies our human ears can't really hear, and it just throws them away. JPEGs do a similar thing for images. And those amazing noise-canceling headphones, they're listening to the frequencies of the noise around you and creating the exact opposite frequencies to cancel them out in real time. It's all Fourier.
And in science, whoa, the impact is even bigger. It's used to solve physics equations that would otherwise be impossible. It helps astronomers decode faint signals from the furthest corners of the universe. It's baked into the very foundation of quantum mechanics, and bringing us right back to the beginning, it's how an MRI machine takes a bunch of radio signals from your body and constructs a detailed picture of what's going on inside. Absolutely incredible. But here's where it gets really deep. For all its power, the Fourier Transform also reveals something profound about the universe. It's not a flaw in the math, but a fundamental, unavoidable truth about reality itself. A cosmic trade-off.
And here it is. You just can't know everything perfectly all at once. The more you zero in on exactly when something happened, the fuzzier your knowledge of what frequencies were involved becomes, and conversely, the more you know about the exact frequencies in a signal, the less you can say about the precise moment in time it happened.
Look at this, it shows it perfectly. On the left, you've got a super short, sharp click. It's very precise in time, right? But look at its frequency recipe. It's just a wide, blurry smear. You can't pin it down. Now on the right, you have a single, pure musical note, perfectly precise in its frequency. But to be that pure, it has to be an endless wave that exists across all of time. You can't have it both ways. And here is the truly mind-bending part. This isn't because our measuring tools aren't good enough. This is a fundamental law of the universe. In quantum physics, this exact same mathematical trade-off between a particle's position, like when it is, and its momentum, which is related to its frequency, is the famous Heisenberg uncertainty principle. It's not just a cute analogy. It comes from the exact same math.
So, after all that, what's the big takeaway? Well, the Fourier transform isn't just a clever bit of math. It is, quite literally, a new way of seeing the world.
It's like we were given a new pair of glasses. It lets us look at what seems like a totally chaotic, messy, complicated world, and by switching to the frequency domain, we can suddenly see the simple, elegant, and beautiful patterns that were hiding there all along. It finds the hidden order in the chaos.
And that really just leaves us with one final, big question. The Fourier transform showed us a whole hidden layer of reality, the world of frequency, that was always there, just waiting for us to find the right lens to see it. It really makes you wonder, what other patterns, what other hidden structures are all around us right now, just waiting for the next great idea to bring them into focus?